Welcome to this explainer. Today, we are diving straight into the intricate relationship between agricultural productivity and environmental variables. We'll be breaking down exactly how macroclimate systems and microclimate factors dictate how, when, and what we cultivate. Let's get started. Here's a quick look at our roadmap. We'll be covering 1. The hydrological cycle, 2. Monsoons and seasons, 3. Light, wind, and temperature, 4. Measuring climate, 5. The greenhouse effect, and finally, Section 6, climate impacts.
Section 1, the hydrological cycle. Let's trace how water actually moves through our farming systems. Step 1 is evaporation from water bodies, alongside transpiration from plant leaves, both transferring essential moisture right up into the atmosphere. And keep in mind, human interventions like heavy irrigation or planting windbreaks can directly alter these rates. That moisture then moves to Step 2, condensation, where clouds form. This naturally leads to Step 3, precipitation. Finally, Step 4 is accumulation. This is where water gathers in rivers, lakes, and vital groundwater reserves, perfectly positioned to be utilized by our crops all over again.
Section 2, monsoons and cultivation seasons. Let's map out the 4 distinct rainfall patterns we see across the calendar year. It's a highly structured cycle. We kick off with the first intermonsoon from March to April. That's immediately followed by the southwest monsoon, which brings substantial rainfall from May all the way through September. Then, the wind directions actually shift, bringing in the second intermonsoon during October and November. And finally, the northeast monsoon takes over from December through February. Now, these macro weather systems directly dictate our entire farming calendar, aligning perfectly with 2 primary cultivation seasons. The first major season runs from March to August, and it's predominantly fed by that southwest monsoon. The second major season stretches from September to February, relying heavily on precipitation from the northeast monsoon. For your exam revision, memorizing this exact alignment between the cultivation windows and their specific water sources is absolutely crucial.
Section 3, light, wind, and temperature.
Let's start with photoperiodism. It's essentially how a plant responds to the duration of light and dark. We divide crops into 3 distinct categories. First, short-day plants. These require short days and extended nights to trigger flowering. Think green gram and cowpea. Conversely, long-day plants, like radishes and carrots, need much longer daylight hours to thrive. And then you have day-neutral plants, such as tomatoes and eggplants. For them, flowering is completely unaffected by day length. A moderate breeze is healthy for a farm, but high wind speeds, specifically anything crossing the 8 kilometers per hour threshold, become highly detrimental. Notice how the damage really compounds. Excessive wind rapidly increases crop transpiration, creating a severe dehydration risk. It physically tears the foliage. It accelerates the airborne spread of pests and fungal diseases. It actively hinders natural pollination, and practically speaking, it renders liquid weed and pest control highly dangerous due to unpredictable chemical drift. Next up is temperature, which directly dictates photosynthetic efficiency. But different crops have drastically different thresholds. C3 plants thrive in cooler environments, hitting peak photosynthesis between 15 and 25 degrees Celsius. In stark contrast, C4 plants have evolved to be highly heat tolerant. Their optimal range sits much higher, between 30 and 40 degrees Celsius. Understanding this fundamental genetic divide is going to be incredibly important for future crop selection as the global climate shifts. Section 4, measuring agricultural climate factors. Accurate agricultural data requires strict physical parameters. If you don't set it up right, you'll get false readings. An ideal meteorological station requires a minimum open space of 10 by 10 meters. The ground itself must be perfectly level and covered in short grass. That specifically prevents false heat radiation from bare soil. Fencing is a must to protect sensitive equipment from animals. The entire station has to be positioned far away from tall trees or buildings that might block the wind or cast long shadows. And finally, the most sensitive temperature instruments are always housed within a ventilated Stevenson screen to guarantee pristine ambient air readings. Inside that station, we deploy highly specific instruments to pull exact empirical data. Rainfall amount is measured by a simple rain gauge. For maximum and minimum temperatures, we utilize a max-min thermometer. Relative humidity is meticulously tracked using a hygrometer. Wind speed is empirically recorded by an anemometer, and solar radiation time, which is essentially sunshine duration, is tracked using a sunshine recorder. Section 5. The enhanced greenhouse effect. We need to make a really clear scientific distinction here. The natural greenhouse effect is a baseline atmospheric process. It maintains the Earth's average temperature at a habitable 15 degrees Celsius.
Quite simply, it's essential for life and agriculture. But the enhanced greenhouse effect, that is a dangerous amplification driven entirely by anthropogenic or human emissions. It traps excessive amounts of heat, completely destabilizing the delicate climatic conditions that global agriculture relies upon. To really understand this enhancement, we have to look at global warming potential, or GWP. If we set carbon dioxide as our baseline with a GWP of 1, look at the others. Methane is 23 times more potent at trapping heat. Nitrous oxide is an astonishing 296 times more potent. This stark numerical comparison illustrates exactly why even marginal increases in methane and nitrous oxide emissions have such an outsized, devastating impact on planetary warming. Section 6. Climate change impacts on agriculture. As global temperatures tick upward, our farming ecosystems face a cascade of systemic threats. We're already observing reduced crop yields as extreme heat pushes plants well beyond their physiological limits. Predictable monsoons are being replaced by erratic rainfall, causing a vicious cycle of severe floods and devastating droughts. Coastal sea level rise is aggressively driving up soil salinity in vital agricultural zones. Plus, a warmer baseline allows agricultural pests and diseases to survive the winter with much higher survival and mobility rates. And let's not forget livestock. Severe heat stress dramatically curtails their overall health and productivity. Let's zoom in on one highly specific and frankly alarming ecological consequence of this warming. Remember our comparison of C3 and C4 plants? Rising global temperatures disproportionately grants an evolutionary advantage to those heat-tolerant C4 plants. The terrifying part is that many of the world's most aggressive weeds are C4 plants, while our essential, life-sustaining staple crops are mostly C3. In a warming world, these C4 weeds will violently outcompete our crops for water, nutrients, and sunlight. Faced with these compounding challenges, agricultural science is responding with rigorous adaptation strategies. We are actively transitioning to cultivating drought and heat-resistant crop varieties. Traditional planting calendars have to be discarded and dynamically adjusted to match shifting weather patterns. We absolutely must expand the use of protected agriculture and greenhouse environments. Field watering is shifting to highly efficient micro-irrigation systems to prevent waste. And all of this is backed by uncompromising soil and water conservation practices. So we've traced the precise interactions between hydrology, atmospheric chemistry, and planetary warming. But as these baseline variables, water, wind, and temperature, become increasingly erratic and unpredictable, a massive question remains. How must the next generation of agriculture evolve, innovate, and adapt to guarantee the security of our global food supply? Thank you for joining this explainer.